Good day, doctor. I am from Group 2, and my teammate consists of me, myself, Jasmine Asinin. I am the leader for this week, and we have Junior Gigio, Keshvini, and Mama Shafiq. So we are from Group 2, and we are going to present the Experiment 6 with the title of Torsion of Bar. So this is the introduction part. Torsional loads are created by propellers on aircraft, transmissions in cars, or by highway signs that are twisted by wind. Torsion loading results in twisting of one section of a body with respect to a contiguous section. Torque is a moment that tends to twist a member about its longitudinal axis. Shearing strains are induced in members under torsion. Shafts are widely used in engineering applications to transmit power from one point to another. A torque is applied to the shaft where the shaft is fixed at one end and free at the other. As a result, complementary shear stresses are developed on the longitudinal planes which cause a distortion of filaments. The purpose of torsion testing usually parallels to that of uniaxial tension test. In this experiment, solid cylindrical specimen of steel or brass will be subjected to a torsional load. During this test, the angle of twist and the applied torque are measured as the test proceeds. From the applied torque, we will calculate the shear stress and shear strain of the tested material. The modulus of rigidity will be obtained from the plotted graph. So we will move on to the theory of this experiment. Shearing strain, gamma, is measured by the change in the angles formed by the sides of that element. It follows that in this first equation, L times gamma equals to P times theta. Then, rearranging this equation, we'll get gamma equals to P theta over L, where gamma is shearing strain which occur on the surface of the shaft. P is the length from the center to any point in the circle of the shaft. Theta is the angle of twist. L is the length of shaft. It also follows that the shearing strain is maximum on the surface of the shaft, where P is equals to C. Gamma max equals to C. Therefore, gamma max is equals to C theta over L, where gamma max is the maximum shearing strain, C is the radius of the shaft, gamma is the angle of twist, and L is the length of shaft. So consider the case of a shaft of length L and of uniform cross-section of radius C, subjected to a torque T at its free end. The angle of twist and the maximum shearing strain are related as gamma max equals to C theta over L. In the elastic range, the yield stress is not exceeded anywhere in the shaft. So therefore, Hooke's law is being applied here, and gamma max is equals to torque max over G. Gamma max equals to torque max over G, which also equals to Tc over Jg. Solving for theta, it shows that theta equals to TL over Jg, where theta is the angle of twist, T is the torque exerted on the shaft, L is the length of shaft, J is the polar moment of inertia, which is pi in bracket C2 to the power of 4 minus C1 to the power of 4 over 32. And G is the modulus of rigidity. So next I will pass to the next member to present.
So, apparatus used in this experiment were a straight rod, a nylon rod. We also have an aluminum alloy, and then a torsion bars testing machine with a lot, We also use a ruler, screwdriver, and also digital caliper. So for the experimental procedure, first the aluminium alloy rod was clamped in a position and the load hanger was placed on the cord. Next, the rotation scale and pointer was set at 400 mm from the fixed clamp and the pointer was set to 0. And then a load of 40 Newton by 5 Newton increments was added and the twist of the specimen for each increment in table 1 was recorded. The load was removed and the rotation scale and pointer was set at 200 mm from the fixed clamp. And then the above procedure were repeated, step 1 until step 2. And then the specimen was changed to the steel rod and the procedure was repeated for the 400 mm length only. All readings were recorded in table 2. And then finally, the nylon rod was clamped in position and the twist was measured for 400 mm and 200 mm when the load up to 40 Newton by increment of 5 Newton was applied to the torsion head. Then the reading was recorded in table 3. Then the load was removed and the full elastic recovery was observed to be occur or not. Lastly, the diameter of the rod was measured and recorded in the table according to the type of materials.
Good day everyone, I am Keshwini will be presenting the result and calculation for experiment 6 torsion of bar. The constant data given is the torsion head effective diameter which is 75 mm. The formula to calculate torque is equal to radius of the torsion head multiplied by the magnitude of the force. To obtain the radius of the torsion head, we will have to divide the diameter with 2 at where the diameter is equal to 75 mm. Okay, for the first type, which is the aluminium alloy rod, the data given is the diameter which is 6.31 mm. So using the formula and steps stated before, table 1 is completed with the result calculated for the torque over 400 mm and over 200 mm in Newton millimeter. The torque value is directly proportional to the hanger load. Next, for the second type of rod, which is the steel rod, the data given for steel rod is its diameter of 4.99 mm and the torsion head effective diameter equal to 75 mm. Thus, table 2 shows the complete data after obtaining the torque with the same calculation method and formula. Next, the data given for the third rod, which is the nylon rod, is the diameter of 6.525 mm. Table 3 shown is complete with the data of the top calculated for over 400 mm and 200 mm with the same method. So that is all for the result and calculation part. I will let the next person to further present on this.
Hello, my name is Gigio, and now I'll be talking about the discussion part. So the first part of the discussion discusses about to what extent does the experiment verify the torque or the twist formula based on the graph plotted. The graph that we plotted was the angle of twist against torque. So according to the graphs plotted, we can deduce that the angle of twist is directly proportional to the torque. And the higher the torque, the higher the angle of twist. The length L also influences the slope, the steepness of the slope. Other than that, from the graph, you can also see that different materials also can cause different angles of angle of twist. So finally, the modulus or rigidity is inversely proportional to the angle of twist, meaning that a smaller angle of twist causes a higher modulus of gravity. Okay. So now let us determine the modulus of rigidity G of our materials today. So to recap, we had three materials that we tested, which were aluminum alloy, steel, and nylon. So all of these had different values that we calculated. So to start off, we calculate the formula of the slope, which is angle of twist over T. So let's take aluminum alloy as an example. So M400, 400 meaning 400 millimeters, it has an M of 0.098. For the 200 millimeters, it has a 0.049 for the M. And then we have to calculate also the polar moment of inertia, which is pi d to the power 4 over 32. So after calculating, we found that the J equals to 155.64 millimeter to the power of 4. And then we also know that the modulus of rigidity has a formula of G equals to L over mj. And then to summarize it, this is the summarization for our calculations. So aluminum alloy has a G400 of 149.62.84 Newton per millimeter square. For the G200 is the same for G400. Finally, the average is also the same number. For steel, we only calculated for the G400, which totaled to 35616.14 Newton per millimeter square. And nylon finally is 3543.57 Newton per millimeter square for G400, 3611.72 Newton per millimeter square for G200, and 3577.64 Newton per millimeter square for the average. So we also calculated the percentage error, which has a formula of theoretical values minus our experimental values over the theoretical values times 100%. So according to the data, the aluminum alloy rod has a percentage error of 42.89%. The steel rod has a percentage error of 54.92%, and the nylon rod has a percentage error of 95.18. This shows us that there are factors and errors that may have affected the accuracy of our experiment due to the presence and the values of the percentage error. So these are the factors affecting the inaccuracy of our experimental data. So the first one is environmental error, whereby the windy environment may cause the unsteady weight, causing the meter scale to not stay in place. So to avoid this problem, make sure that all windows are closed, and make sure that there are no more, or at least reduce the amount of environmental errors that might alter or affect the apparatus and may cause it to malfunction. So this is our second error that we discussed is systematic error, which is the apparatus might be faulty and have several flaws, or it might be worn out, and this might affect the accuracy of the experimental values. So before conducting the experiment, we should make sure that all our apparatus is functioning well enough so that they may not may not contribute to the inaccuracy of the experimental data. So finally is our parallax error, which is the error in reading the angle twist. So make sure the eye level is perpendicular as a reading, so to make sure that the experimental data is accurate as possible. So that is all for my part. I will pass on to the conclusion. Thank you.
Okay, now I will continue with the conclusion part, where the torsion of bars can be applied by torque determination and angle of twist with respect modulus of rigidity. The torque is directly proportional to the angle of twist of a circular cross-section specimen of aluminum alloy, steel and nylon. As we can conclude, the percentage error obtained from G theoretical and G experiment calculations is 42.989%, 54.92% and 95.23% for aluminum alloy, steel and nylon rod, respectively. Since nylon rod value obtained exceed 20% of error, this experiment is assumed as success for both of aluminium alloy and steel rod. Thus, theoretical value can be applied through bending moment calculation. The equation is used to determine the modulus of rigidity of any materials. The average modulus of rigidity obtained in this experiment for aluminum alloy is 14962.84415, 35616.14142 for steel, and 3577.647584 for nylon rod. That is all from Group 2 for Experiment 6 Torsion of bar. Thank you for watching.